So welcome to part 2 of our webinar Wednesday series on transportation electrification for utilities. If you missed our first webinar in this series, don't worry, we're recording each webinar. And if you're interested, I'll show you the information on where to find the recordings at the end of this webinar. So first, we want to thank our Clean Cities partners, the Dallas-Fort Worth Clean Cities Coalition, Land of Enchantment Clean Cities, and the Arkansas Clean Cities Coalition. Thank you all for your support in promoting this webinar. Before we introduce our panelists, I want to take a few minutes to talk about the Clean Cities program. Since transportation is such a critical aspect of our nation's energy consumption, the Department of Energy has offices that focus on how transportation relates to the DOE priorities of national security, economic growth, affordability for businesses and consumers, and reliability. The Clean Cities program falls under the Transportation Integration Division of the Vehicle Technology Office. The VTO develops advanced transportation technologies that fit with the DOE's main priorities of improving energy efficiency, increasing domestic energy security, reducing operating costs for consumers and businesses, and improving global competitiveness of the US economy. Each coalition operates independently, but we all focus our activities in these key areas: advanced vehicle technologies, new mobility choices, idle reduction, fuel economy improvements, and alternative and renewable fuels infrastructure. Each Clean Cities Coalition is fuel and technology neutral. We all work closely with our stakeholders to identify the right fit for your specific needs. There are nearly 100 Clean Cities coalitions across the country. Likely there's one near you. And if you have a project or something that you need assistance with and you fall in one of these areas that is not covered with the Clean Cities Coalition, simply call one that is nearby you. And if they can't help you, they will find someone who can. So our organization is Louisiana Clean Fuels, and we were established in 1997, and we received our designation as a Clean Cities Coalition in the year 2000. The Clean Cities motto, building partnerships to advance affordable domestic transportation fuels and technologies, really says it all. We are a group of people, a coalition, who work together for a common cause, and we build those partnerships and we help find those right connections for you. So in Louisiana, we cover about 57 parishes. And if you fall in that area in New Orleans, don't worry, you are covered by Louisiana, the Clean Cities Coalition. The Southeast Louisiana Clean Fuels Partnership is your Clean Cities Coalition. So while this webinar series was designed with utilities in mind, today we're focusing a lot of our attention on the specific challenges of electrification for the trucking industry. One thing that we have learned this year is the importance of trucking to keep moving goods to market. They truly are our essential workers. While we may be at home working in our kitchen offices, truckers have to keep on trucking so that our stores are stocked with the products that we need. And as we learn more about how COVID spreads, we're seeing evidence that air pollution exacerbates the problem. Whether the virus attaches itself to particulate matter or whether bad air quality simply makes us more susceptible to the virus, we still don't know for sure, but the correlation is clear. Reducing transportation emissions is not just an environmental concern. It's also clearly a healthcare issue. So like Clean Cities, the North American Council for Freight Efficiency is that bridge that helps connect the needs and concerns of trucking companies with advanced technologies and fuel-saving practices that help reduce emissions, which is why today I've invited Dave Schaller with NACFE to help moderate this webinar and to bring that important trucking perspective into today's conversation. So welcome, Dave.
Thank you, Ann, and hello, everyone. I'm excited to be here today. Although NACFE was formed over a decade ago to focus on medium and heavy-duty fleets, if you'll advance the slide for me, Ann, we are now the leading truck organization, nonprofit group working on electrification. We realize that electrification is not only going to take the trucks we normally deal with, but also charging and utilities. And as our engagement director, my #1 goal this year is to engage with each of you that represents one of those charging or utility companies. Next slide, please, Ann. Uh, Last fall, we did a really exciting event called Run on Less. And yes, we used Louisiana, and Luis there was from CNS Wholesale Grocers delivering to grocery stores all across Louisiana, the southern tip of Alabama and Florida. And our demonstration had 10 phenomenal fleets. They provided us their best tractor, best trailer, and one of their best drivers so we could find out how well fleets could truly be with fuel economy. I only tell you this because it leads into electrification here. Next slide, please. The information that comes out of this in the right-hand side, we have our own report about those 10 fleets, trucks, and what they achieved, which was 8.3 miles per gallon versus a national average in regional haul around 6. So yes, that's about a 33% better than that improvement in fuel economy. But we worked in conjunction with the National Renewable Energy Labs and published a free report on what those 10 vehicles would look like if they were battery electric powertrains. So if you really want to know what does an electric truck look like in daily operations and what kind of charging would it need, we've got your answer right there. For those of you involved on the hydrogen side, at the very same time, we worked in conjunction with Ballard and did a report what those 10 vehicles would look like if they were hydrogen fuel cell trucks. So if you're big on providing power into hydrogen, the creation of hydrogen, there's a big opportunity there. If you're on another side of this, we've got a free downloadable data set of the 10 trucks you can use for whatever the fuel is you're working on. Next slide, please, Ann. Part of the electrification that showed up in our demonstration was an electric trailer refrigeration unit. The Meijer grocery stores, I don't think there are any Meijers in Louisiana, but in the upper Midwest, they're all over the place. They are a major big box store with lots of food delivery. They allowed us to film their tractor trailer at their Flat Rock, Michigan facility. And this trailer was there and plugged in. You can see in the lower left-hand side, the cord coming from the wall and the circuit breaker box to the trailer. That when this unit is parked against the building and plugged in, the normal refrigeration unit on the front is a hybrid that can go into electrical only mode so that it doesn't need to draw diesel fuel and can operate quietly, efficiently with no carbon footprint while connected to the building. So it's a very exciting change happening in the industry, but it's one that has its challenges. I was told by one of the leaders at Meijer that most of their stores don't have the power levels available to provide trailers this electricity at their docks. So it takes a major infrastructure change for this supplier. If you want to see more on it, there's a hot link that'll be available, or I can guide you there when you connect with me. Next slide, please. NACFE has been working very hard over the past 2 years to put together a series of reports to benefit not only truck fleets, but charging system companies and utilities. We started out in May of 18 with a report, electric trucks, where they make sense first. And we followed that up with where they make sense first in medium duty electric trucks. The cost of ownership is totally outlined there. And there's a spreadsheet that's downloadable to compare internal combustion engines versus battery electric trucks. From there, we went to the one that will be of most interest to you if you're in the charging utility world, charging infrastructure. Because these vehicles are huge. We're talking about megawatt plus in some cases for charging systems. I know that's got to absolutely bring terror into the hearts of utility planners because they used to see building permits and get at least 6 months to 2 years had noticed that there was a big power change coming, and in the future you're going to be able to order trucks and suddenly need 2, 3, 5 megawatts of power very rapidly. So a real challenge in the utility planning world. The fourth report was on very viable class 7 and 8 hybrid and alt fuels tractors, because there are a lot of things changing in that realm. And just within the past month, we issued the 5th in the series on high potential regions for electrification. Next slide, please, Ann. That report, the high potential report, looked at all the different areas in the United States and covered the technology opportunities in terms of are they a cold or warm climate? Do they have enough traffic or hills to benefit from regenerative braking? What's the electricity pricing and supply in their area? We looked at needs, the also looked at support. How well are certain states doing with incentives and other things? So if you'll flip over to the next slide, Ann, the heat map that came out of all this and the spreadsheet is totally available to you. If you're looking at this going, wait a minute, my state's not lit up like it should be. Well, we've got our spreadsheet available. You can give us your feedback, but the bottom line is quite obviously Northern and Southern California have a lot of incentives and are making more progress than anyone else in medium duty, heavy duty truck electrification. But there are other areas that are prime for making significant success as well in the Dallas, Houston, San Antonio, Texas Triangle area, the Cascadia Range in Washington and Oregon, the Frontal Range in the Denver area, and very definitely in the Northeast. So those are the spots where we NACFE expect to see the most initial breakthrough, but we know that there are electric vehicles going into other areas as well. Next slide, please. Our report on infrastructure. I don't want to go through all the details here, but if you're a utility or charging system company, take note of the lower left-hand corner. The number one thing we want fleets to do is engage with their utility company. It takes far longer to put the infrastructure in place than it will to order a truck in the future. Granted, the trucks are on back order and just coming into production, but in the future that will change. We think it's important for that engagement to start early, and the rest of the path is laid out there for you to study later. Next slide, please. We like to talk about our technology bridge. We're sitting here in 2020, where a lot of these alt fuels technologies are relatively immature. If you look at the bottom, diesel dominates in the heavy duty transportation industry. Natural gas has got a pretty strong foothold, has made a lot of positive impacts, but there are a lot of unknowns and challenges. So we're entering what we call the messy middle, where we are going to be optimizing solutions, making lots of investments, growing infrastructure. We're going to get facts that replace the estimates we're all working off of right now, and we're going to see hybrids of all varieties, battery electric trucks, hydrogen fuel cells, a lot of growth in renewable natural gas, renewable diesel. Somewhere out in the 2040, 2050 timeframe, we see a situation where there'll be fast charging that's much more readily available, long life, low cost, acceptable weight batteries that'll go through changes much like cell phones did. And we'll have commercial battery electric vehicles and hydrogen fuel cell trucks roaming the countryside. But we've got a big messy middle to work our way through, and the truck industry doesn't change fast. It takes decades for us to change because the products have long lifetimes. Next slide, please. NACFE has been around since the 2008-2009 timeframe. We have a very strong history of collaborating with fleets, OEMs, suppliers, dealerships, and government entities, including Clean Cities, Clean Fuels organizations, DOT, DOE, etc. What we are focusing on this year is drawing more people in, drawing in the people on the right. If you're not familiar with all these new OEMs from top to bottom, it's Lion Electric, Tesla, Orange EV, Exos, Neuron, and Nikola. So we want to pull them into the conversations. But we very definitely want to pull in the charging system suppliers, the charge points, EV boxes, green lots, and others. We want them involved in this conversation because it's going to require a lot of development, and very definitely want the utility companies to come in. We know you're very familiar with running bucket trucks. You may have a flatbed to haul foam poles, but you're probably not running hundreds or thousands of trucks as your core business. So there's a lot of room and opportunity to collaborate. Next slide, please. What we're telling the industry is to expect the electrification to go from inside of fleet facilities, their warehouses, their cross-dock facilities, their distribution centers, to go from the inside of the building out. And I'll explain it this way, starting in the center of that target. Electric lift trucks are already in many warehouses. The electric yard tractor that's in the first band there are several hundred of those electric yard tractors already in use in the United States. You don't see them most likely because they never leave the distribution center lot, but they've removed the diesel engine and become electrified. The third vehicle's medium duty delivery, I already talk about that as one of the initial deployment areas. They make sense because they're doing home delivery to your doorsteps. In COVID time, it's even going up more. But we're also seeing the initial field validation units out there for the last two bands that regional haul day cabs that are running things from the distribution center to the grocery stores or other big box stores. And last but not least will be the Class 8 sleeper trucks that are crisscrossing the nation's interstates. So it's coming from inside the facility and working its way out. Next slide, please. We at NACFE have a partnership with a sister nonprofit, the Rocky Mountain Institute. The Rocky Mountain Institute's probably known to most of you in the utility world. They're very much helping the industry with understanding green electricity, whether it's wind, solar, hydro, or other tidal, whatnot, making changes for green energy. And we, NACFE, are all about cleaning up fleets. We've come together and we realize we're at the junior high dance right now, where we stand on the opposite side of the gym from each other. And we might recognize a few transportation players looking at the picture. Yeah, I know UPS and Amazon. I might know Penske, but I don't know who to talk to or how to have that dialogue. So we've put together primers to get some initial conversation going between the utilities and fleets. And if you're interested in doing that, please contact me. I would love to help you make connections. Next slide, please. So right now, NACFE has got the background from Run on Less Regional, our regional haul thought leadership paper. If you want to learn about regional haul operations, we've got that white paper. We've got the guidance reports I already showed you. So right now we're working, we just identified the high potential routes in the US. We're doing it for Canada right now. Very excited to see last night that BC Hydro put out a phenomenal primer paper of their own on electrification for their customer base. We want to support implementation of first and next movers, so we're working closely with Volvo Lights and Freightliner and others on their initial vehicles. We want to scale best practices like we always do and increase the confidence in the value of electrification. Next slide, please. Why would fleets consider electrification now? Well, financial incentives are either in place or they're happening soon that can cover some of the cost of the conversion. So we're encouraging fleets, look into those incentives, grab them if you're thinking about it, because they're going to make your life far more affordable and give you a chance to learn first. But we also know there's a lot of facility reasons to obtain the required power levels from your utility company before all the neighboring distribution centers, since they tend to be all co-located near each other. Be the first, get it while it's there, because the second point, obtaining the power infrastructure can take years. We've heard of situations in Southern California and other areas where it's $1 million a mile to bring in that power. It also might be easier to relocate than to upgrade a facility. So fleets, as they're considering the future, ought to consider whether working with their utility, they're in the best spot or they should be somewhere else. And the physical layout of the lot has to change when you put in the charging systems today. A lot of gravel or paved lots that you can move tractors and trailers around anywhere on. That won't happen in the future. And last but not least, even if you're not real fond of initial electrification, diesel will be changing. In 2021, 24, and 27, there'll be new regulations and technology changes for NOx and greenhouse gases. Next slide, please. So where we NACFE are at, we're trying to help truck fleet maintenance managers, purchasing agents, et cetera, handle this absolute tsunami of disruptive factors that are coming. It's not just electrification, it's autonomous vehicle, greenhouse gases, driver retirement, blockchain, artificial intelligence, and a whole lot of other things that are coming at them. At one utility, I was at the EPRI meeting before the world shut down at Phoenix in March. One utility said, why aren't all truck fleets working on electrification right now? Well, here, folks, there's about 20 other reasons why they're not all asking questions right now. They've got their hands full, and COVID just added more challenge to the tip of the way. So I encourage you to follow NACFE on LinkedIn or Facebook, or get in touch with me. We're here to help and would like the chance to work with you. Thank you, Ann, for this opportunity.
No problem. Thank you so much. Thank you so much, David. All right, so next up we have Ted Bone, the principal engineer with the smart metering and electric vehicle smart charging standards at Argonne National Laboratory. And before I hand it off to Ted, I want to remind everyone to please type your questions into the Q&A, and we will get to them as we go along. Someone may type an answer, or we may answer them live at the end of the webinar. So Ted, you're on.
Well, thanks very much, David and Ann. So for those of you who were on last week, I'm going to back up a few steps and kind of repeat where we left off, just kind of take a segue bridging of the, let's just say the 201 to the 202. Using the metaphor of a snowplow, I don't have enough to pick up all the bits on the path. So there's going to be a bunch of things that are left on the shoulders as we plow through these topics. And then we are going to plow through the topics in the next 20 minutes. And so you're going to have a lot of questions or ideas. That's what this is meant to stimulate thoughts, not answer all the questions, but most of the questions. So you can see the person on the right bending over, pulling the cable a little bit to the side with the cord retriever, that little bump next to his hand. So that's a big thing in my other screen right now, synchronicity. The mega charging system Charin group is evaluating the top 5 of 10 couplers to make this megawatt level charging thing real. So what you see in this image is where we're at now at about between 350 and 500 kilowatt. We're going up to 4.5 megawatt. Next slide. So just following the description of the event, we're going to talk about a little bit on modeling and usage. We're going to talk about CARB rules that are going to drastically impact how we do fleet electrification, including TRUs that David covered in short on shore power, which is not necessarily the charging the vehicle, but supplying energy to reduce carbon footprint. And then also going to have a lot about looking ahead at technologies, V2G and DC as a service. Next. So reminding people, we didn't just get here this new thing. It's been coming over a century. So on the left, you can see things from over 100 years ago, 104 years ago on these buses, electric buses running around town carrying lots of people in fancy wool suits with hard wooden tires, and then, female driver on an Edison electric. And, literally 100 years ago, this one was driving this bus around town. Bus, right? Nothing looks like a bus. Then on the right is Shenzhen. As far as the eye can see, 16,000, and this is old, this is like 2015. So 5 years ago, Shenzhen had all these buses lined up, and they are charging them right now. Next. So this just kind of grounds all the processes we have to talk about today. And again, this is what we're talking about today is utilities have to have the utility connection and load management, but there's all these other things that are part of this. The DFNEA is designed for failure mode effects analysis. All the different things you can do wrong. People using the connector as a ladder. People driving off with the connector plugged in. People snagging it with a boat. Just all the things that can go wrong. There are many failure mode analysis. And then over on the right, you can see cyber everything. People who see an opportunity to both steal energy or steal personal identity information or shut down your charging infrastructure. That has to be prevented. You see in the middle, DC as a service. I'm going to talk a lot about that later. And that's basically reducing your distribution costs. And most of the people in the utility industry know that that's where most of your investments are, is in the distribution and maintenance. Mechanized systems, that's what I was saying the MCS work group is working on right now. How do we actually make these things safe? Because most people say, what do you mean 4.5 megawatt in your hand? In a human's hand? No, in a robot's hand. A lot of people believe it's a robot. Other people believe it's a human. But either way, if that fails, it'll be a huge fireball. So not going to happen. Or personally, you need to prevent that. In the lower center, you see couplers, cables, and cooling systems. Obviously, if we're pushing 3,000 amps, you're going to need cooling. And then in the lower left, you see infrastructure planning services. That's what David was talking about. It's going to take a while to lay out these things, and where do you put all this stuff? Outside the circle are things that are below a megawatt that are important, sub-megawatt, wireless charging, battery swapping, the Chao-G coupler, which again is big, but not as big as the MCS coupler. So if you're going to push a megawatt or multiple megawatt, you're going to need something new. Then in the corner, we're going to talk a lot about, in the lower right corner is the sub-megawatt. Multiple with 20 kilowatt, 200 kilowatt, 100 kilowatt, something that's less than 1 million watts, but significant to get the job done. Next slide. So again, we're kind of backing up what we talked about last week, just so you can think about where we're going. So in the middle of this chart, you can see the GBT and the new GBT, which is called Chao-G. This is what China and Asia are using. Chidemo, to the right of that, is the Japanese and somewhat European standard that's on the decline because, again, it's not keeping up with the Joneses. 400 kilowatt is big, but not big enough. CCS coupler in the middle, CCS1 is North America, CCS2 is Europe. Those we're going to talk a lot about today. The Tesla coupler and then derivatives of that, and then, of course, on the right, that green box, the MCS. You can see, I'm not allowed to show what it is, but I can show a watermark of it. So you can see a thing that kind of looks like a 4 by 4 inch brick with a handle. That's what it is. It's got very large contacts, 2 inch wide by several inch deep contacts, so a lot of copper. So you can see on the top we have the SAIC CCS combination system that can today run a 0.5 megawatt. And so you say, well, but I need 1 million watts. You say, well, then use 2. Just like saddle tanks on a truck. You need 2 to fill it twice as fast. You have 2 fillers. So that can be done today. The mega charging system again runs up to 1.5 megawatt. That's what's going on in my other screen, like right now, like this minute. The next generation of that is being tested in a lab at NREL. Next. So adapters and other alternatives. Shape 3068 as a utility, you should understand this is one of the most powerful developments that's underutilized now, but it offers, it's like the Swiss Army knife. In the middle, you can see that we can push 480 volt, 208 three-phase. You can push 120 kilowatt DC today on the Tesla vehicle. So this side-by-side comparison of the one with 5 pins, which is the Type 1 1772 coupler. In the middle is the Tesla proprietary supercharger connector, same functional pins level. So they can run up to 700 amps on these for liquid cooled version. And on the right is the Type 2, which again is the J3068 with 6mm pins, able to run up to 2 times 160 amps or 320 amps. And that's what you see on the left. Those 2 blue circles kind of show when I pair them up, I can push a lot of current through those 6mm pins. A clone of this, again, a German version of this is about $200. The Asian clone is $30. And so as far as disposable, replaceable connectors, the other CCS couplers and even the ones on the TRUs in the $500 to $1,000 range if you damage them. And again, for the liquid cool ones, up to $3,000. The supercharger, the version that's going to replace the one on the right, that's shown in this early 2018 Tesla prototype, can be up to $10,000. So you can see $30 versus $10,000 is going to be a very different proposition when you're able to run somewhere around 320 kilowatt on something that, again, you won't use anything that cheap. Could be as cheap as $30. So this is a big deal. And then adapters are a big deal. Next. So this is kind of the ins and outs. So most people understand transmission and distribution, right? The RTOs and other operators have to manage these big power lines on the right. This is the one that says 2 substations. Somehow medium voltage gets in. There's that white box in the middle. It says AC to DC conversion. That's the heart and soul of what we're going to talk about in the later slides is how do we make that smaller? How do we not have this be rows or acres of power electronics? And that's what it is now. It's many, many cabinets to get to a megawatt. And then you would say, but I need 200 megawatts. So do I have to have 200 of these cabinets? And the answer is no. It's 4 cabinets per megawatt. So you need 400 cabinets. You're like, I don't have room for 400 cabinets. And you're like, okay, then what are we going to do? Or 40 cabinets, sorry. But the point is that we're going to have storage, generation. This shows microturbine. At Argonne, I have what's called LDRD research money to do compact micro reactors. So 2 to 20 megawatt reactors that sit in a chain link fence. Oop, lost our screen share. Yeah. Must be me. There we are. Unless that was my comment being censored on back. So either way, some people are exploring how can I have enough location-specific resilient, and the key word is resilient. So with natural gas, you have resilience. With PV and battery storage, you have a couple of days of resiliency. And then in the lower right, you see the green thermal cooling line. So you're going to have some kind of cooling if you're going to push these power levels, and then dispensers between these islands. Next. So just reminding people, the power has to get from where it is to where it needs to go. And that's what's going on in this NREL testing event is these yellow circles. How do we get the cable to reach that far, yet carrying 3,000 amps and not accidentally interrupting up to 4 megawatt? So again, arc flash is a big deal. In the center, you can see the big switch gear. In the middle of these yellow circles, you can see a pair of dispensers per cabinet of electronics. And these are each about 175 kilowatt per port. So just to kind of say, oh, I'm going to need 6 of those just to get to a megawatt. It's like, yeah, 6 of those just for one truck at a megawatt. So the front and side are kind of represented here on the left. You can see an island where someone is standing in the middle. You can see there's no bollards here. Normally it would be bollards and other things. But the point is he's got somewhere between 10 and 20 feet of cable that he reaches over, the operator reaches over and plugs into the vehicle. In the next slides, we're going to talk about the overhead, that we have a very tall gantry that reaches down. Thanks, Ann. You can see the tall rectangle on the center left. shows the cable extended and plugged into the bus. On the center or just to the right of that box, you can see them pulled up to the gantry, and then this has 12 charge ports, and then probably literally a mile of conduit to go from the boxes on the left, which are the switchgear and power electronics. Again, most of your utilities, when I say switchgear or panel board, I assume you know what I'm talking about, but these gray boxes that bring in the power and turn it on and off safely, to the power electronics, which are green boxes that convert it from 40 volt or medium voltage to between 400 and 1,000 volts DC. Next. And then the other alternative is up from the bottom. And so Cavitec builds a lot of ground support equipment. You've seen this at the airport of air conditioning hoses, water hoses, power cables for shore power to the aircraft. They are planning on doing this. To the right, you can see Power Hydrants robot, which, you know, not a big stretch that the robot could pop up. See the inlet on the vehicle. You can see in the front bumper of this truck. It would be on the side, on the top. There's many different places you can put an inlet. But the point is the robot can see the inlet, find the inlet, plug in the inlet, and then when it's done, retrieve itself and go back down to the ground. So this, I think, is going to be a very powerful concept, especially when it's tied to these buried bus ducts that we're going to talk about later. Next. And again, I apologize for going swiftly. Main thing is that you kind of get the talking points. What's significant about each of these? So this slide is charging energy as a function of charging capability, or basically power rate. And that's an important thing. Power and energy are not the same. Power times time equals energy. The rate that you can get it in there is important, but everyone says, I need a megawatt, but I can only have a few megawatt charging ports per facility, but I can have many, right? I can have 10x, 100 kilowatt ones. And so this curve on the left, where you can see the 100 on the locations on the bottom index, that has the tan line or brown line on the top, shows that I can get more done if I have more 100 kilowatt stations than fewer 1 megawatt stations. And that's just kind of one of those trade-offs. How many big pipes versus many smaller pipes, assuming that I run the smaller pipes more often or longer during the day. And you can see it kind of knees over on the number of locations that cover. It saturates. So on the left of the 100, you can see that you can always use more, will give you more electrification. To the right, you can see it flattens out, that there's diminishing returns between 100, 150, 200. Then on the right are a bar chart where you can see the tan line and the blue line. It shows that the tan plus blue is better than just a solid blue, just having megawatt. It's just a little smidgen of model. So again, there's hours of stuff I could talk about this, and I think we will in the future, but not today. Next. And again, Fernando's going to talk about this next. So this is just kind of another segue of look, people have mapped out these routes. They have gazillion bytes of data. You can just see on the left, we have 10 1 megawatt stations and 458 100 kilowatt stations. That's what those dots look like. In the middle, it just kind of goes up 50 megawatt stations, 876 locations, and how many routes you can cover. Again, covering these 5 states on the western edge, and again, 100 on the right. Next. So like I said, Fernando's going to cover this in depth, but this is kind of a opening. The TRU is a big deal, and I'll just pause for like a second to let it sink in. If in January 2023, every trailer sold in California or operating in California has to have electric anti-idle, not maybe, must. Every one that is sold, that's a pretty big deal. That's just 3 years away, less than 2 years, two and a quarter years. By 2027 says everything in California, any truck that operates in California will be tagged out of service if it cannot turn off its engine when parked. That's a big deal. So everything that comes across the border from Arizona, Mexico, off the container trucks, anything that's got a transportation refrigeration unit on it has to go into anti-idle. It cannot idle when it is parked near a facility because of air quality. So you can just see that this is an excerpt from this URL. Again, I assume everybody's going to get to see these slides. Hopefully the URL works in the PDF. If not, you can just cut and paste it. But that's the draft right now as it stands. So it's nearly set, as in it's not in stone, but it's pretty firm that these are the dates that are coming. And on the bottom there are some excerpts that kind of explain why. A lot of people use TRUs to park them next to the store for not just the day or for a couple hours, but for weeks at a time. So that's why they would use short power. David already covered this. And on the bottom is, how do we transition to zero emission operation, and how do we do managed charging? Next. So here's some examples. Like I said, I don't have time. I could do hours on just this topic alone, but here's where we are and here's where we're going. So you can see the red post kind of in the middle represents the status quo. A switch, a disconnect box, a blue cable hanging on a hook, a bunch of concrete barricades, and grass and gravel, and a trailer next to it. And David showed the nice new version of it screwed to the building. Most of you know that receiving docks and parking areas aren't quite that nice. They look more like this: weeds, some rusty posts. To the left, you can see the Safety Connect one that has the special connector that has, if you look to the right, you see a cable that's kind of hanging on to the end. There's a trigger mechanism that if the truck does start to pull away, it will pull the latch and pop the connector out of the hole before the truck leaves, so it doesn't tear the cord off the building. So the one in the center, right above the page number, the stainless steel box, each of these has a receiver in it that can be pulled out of the box. So it's meant to be torn out and plugged back in. And then above that, you can see other brands of TRU connection stations that have a similar, basically it's a switch on a lever. It's very low. It's a variation of that switch on a post as a switch in a box. So somewhere between the electric vehicle charging systems that we use for EVs, and this is where this industry is going on smart charging. What do we do when you hit your resource limit? How do you actually manage a bunch of them? So David already showed the Thermo King unit, but the point is these new reefers are going to have this capability built in. Trailer's going to have to be wired. We have a question about legacy systems. What if we have 100,000 or 200,000? Do we have to take all the connectors off and put the new standard on? Do we run adapters? I think the answer is adapters. But the immobilization and safety disconnect are what we're working on J3068 and other work groups within standards. Next. And again, like I said, I could stop for questions, but we'd burn through our hour quickly. So now you say, well, where does this go? And how many trucks is a lot? This to me is a lot. So each of these on the left and the right represents 600 spots that empty and fill every day in Ontario, California. So this is the I-10. To the lower left, you can see where it says MAP is where the airport is. And then to the left are the Penske rental, and to the right are the service facilities. So you can just see there's a lot going on at this off-ramp. In addition to diesel liquid fueling, you're going to have to figure out how to get possibly up to 500 TRU outlets. And it's like, well, that's megawatts. That's many megawatts. And if you think about it, if there's 1 million trailers pulling 8 kilowatt, and again, not all at the same time, that's 8 gigawatt. It's like, that's a generation station. That's another generator that has to go online just to serve all these trailers. And again, conversely, it will displace a lot of carbon, so it's a good thing, but it's a big question mark on how the utilities can support this. How do the facility operators do this? How do we do smart management? So again, this just kind of getting the idea in your head that this is a big deal. And it's coming in the next, less than 7 years, right? 6.25 years. All units, everything crossing the border will either have to have this or have a big red thing that says do not operate in California. Next. So this is a close-up and just kind of the whole idea. There are some spaces that don't have trucks on them now. Now where would we put the charging stations? Where would we put the TRU plugs? Or could the TRU plugs serve both charging and standby? And then could the TRU plug also cover the cabin standby like the idle air units did in the past? I think that's where we're headed on this. Is we have a smart plug, that J3068 plug we talked about, has 480, 600 volt AC, 3-phase, single phase 277, 208, 120, and up to 1,000 volts DC. Same plug, digital communication. So that's a big innovation, and again, on something that, again, in a substandard quality, as low as $30, not $3,000, $30. And then the same with the digital communication. So those are the standards that I work on. I just want to make sure the utilities know that someone's working on this and that it's a pretty big question. And for those of you, the last time we talked about this 300-member utility industry work group that was covered in the last one. I talked about how industry and the manufacturers are working together. If you want to join that work group, you can send a memo to Ann, remember, and we'll add you to the distribution list. The next meeting is ready tomorrow. So if you want to see what's going on in the next 12 months on the slides here on getting deep into it, all the way into the weeds, I have a 2-hour special event and have panel discussions with the utilities, the equipment manufacturers, the site facility operators who own this actual site on what their plans are. So you can kind of get a sneak peek, not sneak peek, you get a direct insight what's going to happen in the next 12 to 24 months. Next. And again, I apologize for going quickly, but this is what we have to do to keep on schedule. So this one is an excerpt from this report published by SEPA. You can see in the bottom the sources are Black and Beach and other surveys on how long it takes. And again, I apologize, the PDF is not a little fuzzy, but you can just see how the number on the right seems to grow with importance. So if you have a 1 megawatt load, it's like adding a new service, like adding a new wing onto a building or a new industrial process. It can happen pretty quickly. no upgrades, just add another circuit. Fly conductor upgrade, right? So you can just add more power to it, but not the grid, right? And that can take place again in between, now and 2 months. For 5 months is what happens when I have to have medium voltage. So the first two are low voltage 480 volt 3-bags. The other one's medium voltage, where you take in a primary service of 13.2 or up to 138 kV. Then typical transformers are limited to 3,000 amps. And that's an important thing to know. It's like when I need more than 2.5 or 2 megawatts, right, but I need 20. Well, you're only getting 2. Like, then what? Well, that's the next slide you're going to talk about. Then, of course, the grid upgrade, you say, this is not in weeks or months. This is years now, right? 6 months to 3 years. And then you can see down at the bottom of, we need a new substation. When you're asking for 20 megawatts, that's long-term planning, right? That's up to 4 years. So you got to plan ahead. So the whole idea is, if you're going to feed 400 trucks in the next 5 years, you need to get your planning going today. Next. And again, I've given whole lectures on just that topic. So here's some solutions. So in the lower left is Hitachi ABB. You can see that they containerize the solution. So all these things that are normally on pad and pad and pad, like you saw with the overhead charging solution for the buses, this one is all pre-wired in a container. And the big thing is that you have your medium voltage connection on the left, and then you have your 12 output ports that go up over and back to each of the buses or trucks in the center, and then some SCADA and storage on the right. So the white cabinet in the middle, it kind of looks like a refrigerator with 2 door handles. That's a rectifier that changes the, I would assume, 480 volts AC into roughly 1,000 volts DC. And the light pink red cabinets, you can see there are 12 slots in there. So each of those are 150 kilowatt output converter that charges each bus. So it's kind of like a rack of electronics. And you'll see later on what other companies are doing. Storage, power, energy, switching, remote monitoring, fleet management, thermal, everything into a pre-wired. So you can kind of see this is going to be really important to get the medium voltage switchgear, transformers, everything as turnkey as possible to reduce your labor costs and, of course, your site footprint. The good news is this is like 2.5 megawatts. The bad news is you need between 25 and 200, right? So you're like, does that mean I need 10 of these? And the answer is yeah. 10 to again, you just wouldn't do it on doing 100 of these containers, because 100 of these containers just take up too much space. But that's just to get your mind wrapped around. Here's what a 2.5 megawatt turnkey solution looks like. Next. DC as a service, I mentioned it before. This kind of grounds the concept. Some people can look at this and know exactly what they're talking about. Other people, it takes them a little while to figure out what that squiggly lines are. But you can see on the bottom, we have the AC power conversion that goes into a medium voltage switchgear, which goes into a bunch of parallel converters. It goes into a DC load center, then goes into the distribution units, and then out to the vehicles. That's pretty much what we just saw in that container. On the top, there are 2 rows. Top row shows the AC solution using medium voltage to low voltage. So you have your distribution feeder of your medium voltage, those blue power lines we saw about 10 slides back. Medium voltage switchgear, again, it's not small. It takes up the size of a car parking spot. It's not small. Then the transformer, as you know, that can take up the size of another, a light-duty vehicle, a sedan. Right? It's not that big brick of steel and oil takes up space. And then we get the 40 volt, and again, that 2.5 megawatt service, that's an important part, right? That limitation is kind of a showstopper for some people. They say, well, I only need 2. Good to go. They say, but now I need 3. Well, 3 is more than 2.5, so you're going to need a whole nother system, everything from left to right. And then again, the AC to DC conversion, which are the battery chargers, and then the charge ports and the dispensers. So the light blue one below that shows the future, or where we're at now, basically status quo, but it's not a done deal. It's a pilot. So we have our distribution feeder, goes to medium voltage. That medium voltage goes directly to DC, cuts out a whole bunch of steps and equipment, and that's called a solid state transformer. Then to the right of that, we have low voltage distribution centers. This is what we'll talk a lot about in the coming slides. The DC to DC converters, which are the dispensers, and then of course the charge ports and the electronics. So again, just cuts out a few steps and makes it scalable, that in the middle where that first red arrow is, if I just keep adding on more to the left, I can add more source, and then I add more to the right or more distribution. Again, there's diminishing returns. I can't put 1,000 trucks on one feed, but I can put tens or hundreds on one feed. Next. So that's the concept of DC as a service. Again, the idea is that the utility owns all of this. That's important. So on this diagram, it's the same thing, but more hardware-ish. In the middle, you see transmission distribution. That's normally where your primary meter is, in that first M in the center, just left of center. And then the medium voltage breaker, that's always got to be there. That's your safety device. And then the solid state transformer. So again, this can be everything from the size of a chest freezer to the size of a semi-trailer or multiple semi-trailers. So that idea that I take medium voltage to DC, again, just thinking about the numbers, if it's 13.2 thousand volts down to 1,000 volts DC, or 1,300 volts, that's a 10-to-1 turn down ratio. Not that big. And again, that's the big deal about distributing it at above 1,000 volts DC. 1,000 to 2,000 volts, you'll see in the subsequent slides. So this is what I'm going to do. So this is just make no bones about it. This is literally the equipment you see on this page is what I'm going to screw to the wall and run at a megawatt in the next 12 months. And so this busway you see on the right, this thing that kind of looks like a big door rail hanger, whatever I call it, that's called busway. It's used in a data center. It has 4 poles that are good for 400 amps each, or a 2-pole system that I can run at 800 amps at 1,250 volts. And again, just to be technical, this is only rated at 1,000 today, but I'm going to run it at 1,250. But that gets me a megawatt. So something that's about 6 inches square and up to 300 feet long, I can just keep adding on more boxes. So you can see the tap box in the middle, these kind of fingers that reach in there. And looking at the 20 kilowatt converter on the left, the math is simple. At 1,250 volts, 20 kilowatt is only 16 amps. That's 14 gauge wire. Think about it. I feed my vehicle with 14 gauge wire. And a lot of people say, oh, that's how we do distribution systems now. So that's true. Just think about the distribution systems over your head or buried lines, but now on a busway, or you're going to see some bus ducts and other ways of getting the copper into something that doesn't look like a spaghetti mess of conduit. Just going around the circle, we can see on the left the 20 kilowatt DC converter called Wolfspeed is a silicon carbide transistor manufacturer. They want to sell transistors. So they have put out a reference design. I'm building a batch of maybe 20 of these, and we're going to connect as a system that looks like this row across the bottom that has all these parallel boxes that have battery symbols in them for different things. Batteries for vehicles, batteries for stationary storage, PV, photovoltaic. You can see that 3068 connector, but the 99% is a big deal. If, and again, IF question mark, you can run at 99%. That means I need no external cooling. So that steel box you see in that photo is it. No heat exchangers, no filters, no maintenance. Oh, can you go back? So that's a big deal, unless you're telling me to move along. But I think we got 40 minutes left, so I think we're in good shape on time. But the point is, 99% doesn't just make it. Go back. Make it convenient. Okay. Like I said, I hope you're not telling me something. But so not just convenient on energy, but it enables a whole bunch of mechanical systems to become much smaller and cheaper, much like the power supplies on your phone charger and other things. When it's the size of an ice cube or whatever, cassette tape, very, very small because of the high efficiency. And again, it's not just about the energy, it's about the thermal and mechanical and mean time between failure. So going around, you can see that this will be used as a charger. Like I said, I'm going to build a bunch of these. 20 kilowatt blocks gives us the ability to charge 50, class 4 to class 8 if you have enough time, vehicles, right, in parallel on one of these pieces of busway, like 50 on one 6-inch, rail. That's pretty good. 50 is a long line of vehicles, right? 50 can be an entire delivery fleet on just one of these. So the power supply in the upper left, again, is only 18 kilowatt, 20 kilowatt. This is the whole idea of safe, right? So we only fly 2 feet off the ground. You don't take your prototype up to 10,000 feet on the first one. You fly 2 feet off the runway and see if you can go left and right and land safely. So after we kind of successfully run at 2 feet off the runway at 20 kilowatt, then we start to go up to 200 kilowatt, 2 megawatt. But again, only fly as high as you want to fall. I'd rather blow up a $2,000 piece of electronics than a $200,000 or $1 million piece of electronics, again, because of controls. So these dotted lines, these red dotted lines are communication protocols. The little M's are meters. You can see literally in the palm of my hand, that's why it says dot, 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 meters on hand. Literally on my hand are a bunch of these meters, and these meters are everywhere for both revenue and controls. So again, the DC as a service is about the utility, and if you just draw a horizontal line below where all the row of M's are, in the center of the thing, that's where the utility is doing the transaction. So that is my premise. Everything above, the utility gets to own and manage in the best interest of the stability and operating cost, and of course that aggregated load control, especially when I can do bidirectional flow. So these DC converters allow seamless flow into and out of the batteries on a millisecond response level. So that's a pretty big innovation that comes along at 99%. So the round trip of that is 1% in, 1% out. I only lose 2% on the transaction plus whatever the battery losses are. So in the lower center, you can see emulators. Again, I'm not going to risk $1 million vehicle or $250,000 vehicle. I'm going to use these big loads. So what you see there is a 500 kilowatt load bank and a bunch of 6 kilowatt modules that act like a vehicle, but is a very safe way to do it. So moving across, you can see the photovoltaic, the blue tiles on the roof. So that's literally the roof that I'm using. So that section's about 35 kilowatt. So again, I can easily peel off 20 kilowatt of that, put it back into this busway. With this on the right are these DC converters that from Intergrid. And so that battery, the Leaf battery used, is about $1,500. The DC converters about $2,000. For about $3,500, and again, I can have another one on the PV. You can just see in this single thousands of dollars per node, you can have a pretty good test bed. So this is what the takeaway of this slide is. Up to a megawatt, 20 kilowatt building blocks, right, on things that are in the singles of thousands of dollars per node. Next. So this is a little bit, going up the food chain. Delta Electronics got a couple $1 million FOA, a government grant, to build prototypes like this. So you can see in the bottom center are their first year pass at how the modules will look. On the left, I put a motor control center. So some people know what an MCC is. Other people say, I have no idea what you're talking about. But in there are fuses and switches, and this thing on the lower left is called a bucket. So those bricks slide into this frame that's above that. You can see meters and other indicators, but most of these are basically a box with a switch and some other stuff in there. Well, that thing is, roughly about 20 inches cubed. And on the right, you can see something that's 33 inches deep and about 7.8 by 7.8, but roughly 8 by 8 by 33 inches deep. The red part in the back is the medium voltage, so the 15.2 kV input. The little step on the left in that anodized box is a DC out. So basically that block directly above it that says SFT, these are solid state transformer modules. They're 50 pounds each, so you can pick up each one and put it in the hole. And you run a whole bunch of them in parallel. So you can see each one per phase. You connect each one to a different phase leg, and then you have a whole bunch in parallel. So you can just imagine row after row, rack of these. When one fails, you pull out that one that has failed, almost like a valve, and you put it back in. So, and then in the middle of the two blue boxes above, you see 1 kV DC bus, right? So they're going to run 1,000 volts. Some people are talking about running 2,000 volts. In the lower right, you can see what we had in the previous one on photovoltaic and battery nodes that are connected in parallel with the solid state transformer. And then on the right are the chargers. So these parallel, there it is. Okay, now I can see it again. That black box in the right, that's 79 pounds. That was the takeaway. So now I can finish my sentence. So next slide. So the question is, how do I connect all these things? And this is just kind of one of those graphic things that anybody who's done a project can say, yep, that's what's underneath all that concrete. Row after row of conduits that have one circuit per conduit. So these are about 3 or 4 inch conduits, lots of them. And so when I need to do megawatts and each switch has a circuit, that's a big deal. But I don't see that on the overhead distribution lines. I see 4 lines, my 3 phases plus my neutral go over, and then there's taps that come off to go to my low voltage transformer, and then from there there's other taps that are in parallel to have 6 houses or whatever the breakdown is that are tapped off of wires. So a wire with an insulation piercing tap that feeds multiple circuits. It doesn't have a conduit and a disconnect. So on the right are these bus ducts, and this is how the photovoltaic world works. This is basically what real people do. They say, I have megawatts of photovoltaics. How do I connect all these things affordably without it? You just don't see a ton of conduit coming off a PV array. You'll see this thing. So you can see that it's aluminum frame that has some plastic discs that go in that hold the conductors away from each other. So again, as you can imagine, if you bundle it in a conduit, you get less performance because you have to derate for heat. But when you spread it apart and you say, look, I got a mesh cover that goes over the top and the bottom, I let all the heat go right through. The other question is all these bends. You can see on the left all the elbows. Just how much space that takes to bend, 1, 2, 3, 4 times 1, 2, 3, 4. So that's only 16 conduits that make that bend. You can see that the same number of conductors are in this one and the one in the lower right. It just goes down and under the ground and around. So this is the way I think that this future is going to go on DC as a service. Duct banks. Next. we're in the final stretch, so I think we're on time, and I'm just going to assume that Fernando and we're going to have enough for Q&A. We'll just kind of round the finishing turn on this topic of bidirectional. ISO 15118-20 allows bidirectional flow, the communication standards between the vehicle and the charging infrastructure, to export power. The names of the services of peak shaving, most of you are utility oriented, so you know what I'm talking about. It's not really one of the things. Increased self-consumption, to say, I don't need to export, but any resource that's behind the meter, how do I actually do that to service? And you can see they have the residential customer logos versus the utility customer versus the industrial customers. Again, just the icons on this chart. This is from BMW on what they're going to do with their grid-connected vehicles. The arbitrage, right, are these intraday, so multiple days, I'm figuring out where my loads and sources are, and that it's centralized control versus localized control, pilot operations versus laboratory versus concepts, right? So again, these are things that are going on. It's just food for thought. How do I do this? OCPP is the Open Charge Point Protocol. Almost all charge stations have this protocol. It allows for energy management in both directions. And then FERC, anybody who knows what FERC is, in Order 2222 allows aggregators to take all of these things and bundle it. And that's a big deal. And so all this EV charging is specifically called out in FERC 2222 on how can everybody bid on grid services. Next. And my last slide is port electrification. So we have all these ships coming and going, and there's a demo with 33 yard tractors at 175 kilowatts, so 5.5 megawatt of managed load to diminish that. So this is the handoff to Fernando. Thank you.
Thank you so much, Ted, and I apologize for the technical issues. I had a cat jump on the computer earlier. Okay, so our next speaker is Fernando Garcia. He is the Vice President of HDR. Welcome, Fernando.
Thank you, Anne. And if we can go to the next slide. So today I'll be talking about the West Coast Clean Transit Corridor Initiative, and a quick link to the initiative is right there. If we go to the next slide, I wanted to share a little bit about HDR before we get going. We are engineers, architects, scientists, economists, and communicators, and we work on providing solutions to the world's toughest challenges. We've been around over 100 years, and we are employee-owned. We have over 10,000 employee owners in over 200 offices in the U.S. and 13 other countries. Let's go to the next slide. And we operate in 14 different markets, and this slide showcases the cross collaboration that we can bring into the tables on projects like this ones, like this study, where we bring experts from our transportation group as well as experts on our power side. Next. So I wanted to talk about the report. So on the reports, on the study, what we did is we seek out to get together a roadmap to electrify highways, specifically for medium-duty and heavy-duty electric trucks. And the study is looking at the 3 states of California, Oregon, and Washington. And we started mainly looking at the I-5 corridor, which is over 1,300 miles, starts in the border with Mexico, all the way up to the border with Canada. And we also looked at the intersecting routes. We started on January 2019, and we ended up roughly around February, March of this year. But with COVID and everything, we ended up releasing the report in June. So that helps provide a little context on how we got to the finish line. Next. The study was sponsored by 9 electric utilities and 2 agencies with over 20 municipalities being represented. And the sponsors are shown on the right-hand side of the slide. The consulting team that worked on the project includes HDR, and we had CalSTART, S-Curve Strategies, and Ross Strategic. So we had a really large team with a lot of great input on both sides of the table, and it was a fantastic exercise. Next. So we put together quite a bit of information. It's I think over 200 pages long, and what we ended up deciding is we split the report into a report and a tech memorandum. In the report, we looked at some research on policy. We looked at projections of electric truck vehicle sales, and we also looked at a network of along the I-5, and I'll get to it here shortly. And eventually we got to the recommendations on the study, which is a proposed network of charging, public charging sites, specifically for medium duty and heavy duty. On the next slide. So the technical memo is where we gather up all the information. We did some research on technology around electric vehicles. We reached out to a wide variety of stakeholders, including fleet owners, fleet operators, OEMs, charger providers, and of course, electric utilities. We also looked at the existing truck market, and ultimately, we also looked at the existing and planned charging infrastructure programs that are available with utilities. Next. So this is a little bit of the road that we traveled to get to the end, to the recommendations on the study. But where we started is we started looking at, how many trucks do we have on the road, and that's basically what the table on the right hand side on the lower tells us. How many trucks are in the States, and how many vehicles, how many trucks are being sold? So on the left side, we looked at the latest sales that were available to us, they were 2017, and the sales of trucks in the 3 states, California, Oregon, and Washington, were approximately 11%. And what we did is we have a ton of tables. We ended up not being able to show all the tables because it was just too much information. But on the report, we tried to highlight as much information as we could, and we put all the projected sales into 2030 for the different classes, class 3 to class 8. And medium duty we classify between class 3 and class 6, and then heavy duty is class 7 and class 8. And the projected number that we looked at for sales of the regular trucks is basically about 11% in 2030. And at the moment right now, in the 3 states, in 2017, we were looking at approximately 1.7 million trucks on the road in the 3 states, and I think that number is closer now to 2 million. So next. So then the next step that we did is we basically started looking at let's do a projection of sales of electric trucks, and that's what the figures on the right side. We did those by state. We did those by medium duty, which that's the figure on the upper right-hand corner, and we also did it for heavy-duty electric truck sales. So we basically put together 4 different scenario models, one driven by adoption rate and the other one driven by incentives. And as you can see on the upper right-hand corner, when we have incentives that can be used for making purchase of these vehicles, basically getting some rebates, getting some grants. Those having incentives really is a big driver for adoption, and you can actually see it on both graphs for medium duty and heavy duty. Our forecast number 1 is basically the most conservative, and forecast number 4 being the most progressive. But ultimately, with number 4, what we can see is that 3 and 4, the incentives have they are a big driver for advancing electrification. And then another interesting component is looking at the bottom right-hand corner, is that adoption really starts to take off for heavy-duty trucks. And these are projections based on the data that we gather. But we're looking at an increasing adoption for heavy duty ramping up in 2025. And this date has an important component that we'll talk a little bit more about it here as we summarize the report. Next. So one of the other components that we looked at is we gather a bunch of data and we put it into a GIS database, and part of the data was looking at the truck volumes, and we were looking at the annual average daily traffic for both medium duty, heavy duty together, both medium duty and heavy duty, and we have a wide variety of graphs. We were looking at what is the existing truck traffic looks like along the corridor, and that's what this figure depicts in 2017. And if we go to the next slide, we also did some projections. What will the truck traffic look like in 2030? And you can kind of start to see where some of those bottlenecks and some of the areas where we're actually going to potentially see some significant increase of the daily traffic along the highway corridor. Next. So another key component that we were looking at was we put together a heat map and we looked at freight activity centers along the corridor. This is basically composed of warehouses, distribution centers, storing goods, and transportation of passengers and cargo. Ted showed a large number of trucks and trailers along the highway. I think it was either the I-10 or the 60. And this is basically the same type of information. It highlights the heat maps based on that. We also looked at truck stops and parking areas because we think that these are good opportunities for electrification. And another component that we looked at was we identified the number of electric substations along the corridor in the GIS map, 5 miles east of the I-5, 5 miles west of the I-5. And we also put the existing public charging infrastructure for DCAAS along the corridor. We ended up not using them because of the limitations. Those are not necessarily designed for medium duty and heavy duty trucks, but we ended up showing them on the map just so it can get us a good interpretation of what's available right now. Next. So the next component on that table on the right-hand side is fuzzy, and you can get it out of the report. But we basically compiled data on all the available trucks that we knew were on the market. This is early 2019, and I know CalSTARS is doing a great job keeping up and updating this list. But another key component that we were looking at is we were looking at the specs of these vehicles. What is the range? What battery size do they carry? That way we know how much energy they're going to require and how far these trucks can travel. Next. And then what we did is we started to look at what would be the optimal state of charge for these vehicles. And we basically have a lower limit and an upper limit. The lower limit, we ended up settling at 25%. It could be anywhere between 15 to 25%. And it's basically how far, we want to go with battery discharge. And we don't want to get past 15% because potentially, we could damage the battery. But we ended up selling at 25% just to be on the safe side. On the upper limit, we're looking at 80 to 85%. And this is basically how fast can the chargers put power into the trucks without slowing down. And we, through different studies that have been already been completed, we know that anywhere between 80 to 85% is when fast chargers starts to slow down. So basically, this optimal state of charge gives us the ability for a truck to come off when they need to, charge as quickly as they can, and then hop back on the road. And the table on the right-hand side is basically a quick average summary of the mileage by this optimal state of charge. What we ended up looking at was for medium duty, the lower limit for class 3 vehicles was 49 miles. And the lower range for heavy duty vehicles was approximately 127 miles. Again, this is based on existing available data and data of vehicles that are supposed to be coming into the market. So what we ended up selling is, again, going back to that 2025 inflection point when, heavy duty electric trucks really start to take off, and we segmentalized the market. We said, let's look for a solution for the medium-duty electric vehicles that are going to start traveling along the highway, that are already on the highway, and let's look at how can we support them between now and 2025. And then after that, between 2025 and 2030, and even between today, because some of those vehicles, those heavy-duty vehicles are being tested, how do we support that market? And so that's why we actually separated the two of them between medium-duty and heavy-duty. One of the key components that we looked at is, well, if the optimal state of charge for medium-duty, the lower limit is 49, then we should look at putting public charging infrastructure no less than 50 miles apart. And on the heavy-duty side, looking at the lower side, 127 miles, then the same thing applies. What if we do 100 miles? And what if we leverage the time that we're spending to plan for the medium-duty charging stations, and we plan right now because we know we're going to need to make an expansion for heavy-duty charging infrastructure. So next. So the next thing that we looked at is we looked at our projection of how many vehicles will be on the road. Again, these are projections, these are forecasts. For 2025, for medium duty, we're looking at an average of approximately 4.4 electric vehicles on the road, electric trucks, as basically class 3 to class 6. And we have 0 there for heavy duty. It's not 0, it's just a small number. And then we applied the same type of projection for 2030, and we arrived at a combined 8.3% number of electric vehicles that will be class 3 to class 8 on the road by 2030. Next. And this is a busy slide, but this is basically where we arrived at. We arrived at a network, proposed network of charging stations along the corridor. Those charging stations are said to be for medium duty, to be planned and designed and hopefully operational. This is a study between now and 2025, so we can support those medium duty vehicles that are traveling along the highway. And we ended up at that 50-mile range. Based on the research that we did on the technology, we proposed 10 charge ports at 350 kilowatts, which is something that's readily available right now. It's not the most common, but we felt that in the next couple of years, they will become more of the norm, somewhat like how the 150 kilowatt charger is now sort of the norm for electric trucks. And looking at that, we have a peak load for those charging stations, medium duty. We're looking at 3.5 megawatts of peak load. And then on the 2030 projection, the goal will be to co-locate charging stations specifically for heavy duty, and utilize the planning and the time that took to get those medium duty sites. And we will do basically every other one of those, every 100 miles apart. So along the I-5, we ended up with 27 medium duty sites, and eventually being able to expand 14 of those approximately every 100 miles to make sure that we can get the heavy-duty charging stations. Next slide. So, in conclusion of the study, what we have, we identified the different challenges, that currently exist. The figure on the right-hand side is similar to the one that Ted has. Is actually close to Corning, California, and you can see the I-5, you can see the 99, you can see hundreds of trucks, 3 basically truck stops, and there's a lot of challenges in the sense that there is a lot of variables that need to be taken into account: equipment selection, site location, distance from an electric utility interconnection, how much capacity there is on the electric circuit. Permits can be a challenge. So another one is the public funding that we have had has been mainly on vehicles and the private infrastructure, and it will be ideal if we can actually get some of that funding for public charging infrastructure. We also identified some knowledge gaps in fleets and getting to know the total cost of ownership, what kind of impact in operations range has with their fleets. We also know that in urban areas, there could be some challenges trying to get, a really large charging station. The interesting, when we had the conversations with the utilities, the interesting part of this dilemma here is that industrial zones usually have a very sturdy distribution grid that can actually accept the loads. The challenge there is that there are limitations with space. And then the other challenge is, the length of time that will be needed to go through the planning process and the design, the permitting, and eventually getting this public charging infrastructure energized and operational. Next slide. So some of the key findings from the study was that we continue to see a growth of medium duty and heavy duty electric vehicles. More products are coming up on the market. And we continue to see clean fuel policies they basically continue to play a key role in driving adoption, especially too with CARB and the truck rule that, by 2045, all trucks that are sold in California need to be zero-emission trucks. The other key finding is that, private funding, state, federal funding for charging infrastructure can play a key component for driving adoption. And you can actually see that in the forecast that we were looking at. Also, we see through the stakeholder engagements, fleets share with us that having a network of public charging infrastructure is something that they will benefit from. And so that's also important. And ultimately, a study like this can drive a network of public chargers that can have, that can standardize what equipment can be used and how, no matter along the corridor, make sure that they all look the same. Another couple of key findings. So we talked about the mileage range, so I won't go into those. But the last two bullets are important. Some of the feedback that we received through interviewing the electric utilities is when we're talking about a relatively small load, we're talking about a peak load of 3.5 megawatts for medium-duty charging station. Most utilities can accept that load increase. Obviously, it all depends on how far along you are from your circuit, and in some rural areas, that can be a challenge. It also depends on how much capacity is in the grid. But overall, the feedback we received is 3.5 megawatts. We can handle that. And a project like that, I know Ted showed the CEPA report, which has different timelines. It could be anywhere between a year, 2 years. It has a wide variety of factors, but ultimately not a huge deal. Now, when you start talking about potentially what 23.5 megawatts would look like, in fact, 10 megawatts plus, and you start thinking about what that could look like for the grid, that is where we can see a significant impact. Ted talked about the megawatt charger, a megawatt, 2 megawatts, and eventually, anything over 10 megawatts could take a significant amount of time. Based on the feedback we received, it could be anywhere between 3 to 5 years, and this is between planning and getting the charging sites operational. And the last slide that I have here is, what are the recommendations for moving forward? So we were looking at, a begin long-term study planning that can look at the detailed evaluation of these sites. So this is the first step, but we really need to move into a second step and look into all the details and do a dive in so we can identify all the different components and ultimately make sure that utilities are not a barrier to advancing electrification, especially for a network like this. The next one too is that, collaboration between stakeholders is extremely important, and electric utilities can be that trusted energy advisor. And so engaging the different stakeholders to collaborate and work through, partnerships and pilots is an extremely important component for making a network like this happen. And lastly, I think it's important to leverage the expertise that electric utilities bring to the table, so they can help support the business case for advancing electrification. Electric utilities need to be at the table. They play a key component, and I think that's one of the important components of the study, that with the help of the utilities, the different stakeholders, we can come out and develop a business case that can help manage the overall cost, so a network like this can become a reality. And that's, I think the next slide is just my contact information, but that's pretty much it. Thank you.
Thank you, Fernando. Awesome. Okay, so we don't have a whole lot of time for Q&A, so I'm going to turn it right over to Dave Schaller. And if y'all don't mind staying an extra 5 minutes, we'll try to get in all these questions. So take it away, Dave.
Okay, you can hear me?
Yep.
First question, is there a standard connector for TRUs? Ted, can we call on you for a very short answer to that one?
Well, that's my favorite joke. Standards, we got hundreds of them. So basically, people are using the IEC certified 4-pin connector, and then you saw the Safety Connect, which is a 6-pin connector that has a pilot. And then again, SAEJ 368 is a standard, but very few companies besides like Volvo and other port electrification activities have used. So again, not the biggest one is the one we showed, which is this IEC plug on a basically a box with a switch. But you can literally disconnect a live 480 volt circuit and have a huge arc flash. So there's no safety, or just standard extension cord safety. So you get what you pay for. You can have a dangerous system with an IEC, NEMA plug today, but that's a bad thing, and there's no smart management. 3068 is the way it should go, but again, only a few people have drunk the Kool-Aid so far.
Thank you, appreciate it. Next question, did you include truck home bases? Much charging would be done there. Do either of you want, I'll take a quick shot from the NACFE aspect. We believe a lot of the initial truck electrification work will be done with home-based charging. That there is, one way to look at this is there are trucks built with day cabs that you can't sleep in, and there are trucks built with sleepers. About 45% of the market are day cabs, so no one's sleeping in them. They're generally not gone overnight. So half of the trucks are home most likely every single day with a potential for recharging unless they're running 2 or 3 shifts. So we see a lot of the initial industry being home-based charging. Fernando, did that come into the planning efforts as you looked at the I-5 corridor?
Yes. In fact, I also agree, with your assessment, David, and we, the work that NACFE has done, we included information from the NACFE reports as well too. Yeah, it's an important component. Most fleets right now are looking to plan for the long term, and what we see right now is that home-based charging being the beginning of that transition. But eventually, we also see a need for public charging infrastructure, specifically, for the vehicles that are going to be traveling along the highway. So eventually, as what we see right now is an immediate need to have home-based charging, but eventually transitioning out to be able to have that infrastructure along the corridors to be able to help anyone moving along use this infrastructure. So I think it's both. But yes, I agree that at the beginning, what we're going to see mostly is a home-based charge. The other key component too that I think is important to consider is, those private fleet owners that have a couple of trucks, and they are going to be making a huge investment into making that first purchase and making the transition. So public charging infrastructure would help avoid some of that capital cost from an investment perspective, and that's one of the feedback that we received during the interviews with some of the fleet owners.
Thank you, Fernando. Appreciate it. One last question we have here. Why would BYD design buses to charge with 80 kilowatt AC instead of 80 kilowatt DC? Does it reduce infrastructure requirements? Ted, would you like to take a shot at that, please?
I would, and it's a matter of who pays. So when you put in liquid fueled buses, you usually have a big fuel tank or some kind of depot that has a big hose. And per bus, you just have one hose for possibly your whole fleet. So the per bus thing is kind of where this aims, is like if I have to have one charging AC connection per bus, that's the lowest. If I have a system-wide, like I said, if I'm doing 100 buses and I do a system installation, the per bus cost can be lower for an off-board charger than an on-board charger. So that's really what it comes down to, is what are your assumptions on what you're going to invest in your facility versus what are you going to invest in the recurring cost on each bus.
Thanks, Ted. Appreciate it. I can tell you from the workshops we've been doing, one of the aspects that's scariest is not the first implementations. That as fleets put in 1 or 2 vehicles, yeah, we can work together and we can collaborate and get a charging station. The really scary part is if those pilots go extremely well and all of a sudden, instead of 1 or 2, the numbers are 20, 40, 75, then we're talking about phenomenal changes in infrastructure and challenges. So the future will be quite interesting, and we'll all need to work together to make it work out. Anne, back to you.
All right, so thank you all so much. There's one more webinar in this series. It was originally intended to be the first one. It is a nice basic introduction to transportation electrification for utilities, and some considerations of how to get started, how to have your own incentive plans and programs to incentivize electric vehicle ownership and charging infrastructure development. So that is next week at 10 a.m. Central, and we will send you all links on how to connect to that and how to register if you're not already registered. And we have another series that goes into the fleet perspective. EV Market Watch, we have Daimler and Volvo and Orange EV, top executives for each of those organizations talking about the vehicles coming out. And for the Fleet Electrification Part 2, we have one of Fernando's colleagues at HDR, Robert Moat, and we have Mary Till with Swatch Group, who are going to be giving some great advice to fleets who are really interested in getting started. Even if you're not a fleet, both these webinars would be great for you. And again, just wanted to thank our Clean Cities partners for helping us to promote this event, and we will have a recording of this webinar available for all of you. Thank you very much. And this concludes our webinar today. Thank you.
Thank you, Anne.
Thanks.
Bye, y'all.
Thank you.